Understanding physics, graphs. I'm going to talk a bit about graphs. Now, plotting a graph is often the best way to investigate the relationship between two variables. If we plot our data on a graph, then we can see what the trend is. We can investigate the relationship between two quantities. Now, looking at these graphs, you should recognize these. You should be able to look at these and say what the relationship is. So I'll be quiet for 2 seconds if you want to pause the video and have a think. The relationships are, well, in the first one, the two quantities are proportional. Y equals kx. Obviously, if you want to nail down the relationship, then you're after a straight line. Okay, physicists tend to be very lonely people. We're always looking for good relationships, and we get very excited when we get a straight line. The second one is an inverse relationship, y equals k over x. The third one, top right, very important one, it's called an inverse square relationship, y equals k over x squared, inverse square. Can you see the difference between the inverse and the inverse square graph? Bottom left, we have y equals k times x squared, is very common. And then the next two, the last two, y equals sine x and y equals cos x. Very important that you notice the difference between them, sine x and cos x. I'm sure you probably do A-level maths as well, and this is all pretty basic stuff. Now, this graph looks like an inverse square relationship. How would you actually confirm that it is? Now, if this was in practical work, what you would do is you'd have your data on a spreadsheet and you would plot a graph with the spreadsheet, because it'd be very quick to do, of y against 1 over x squared. And if you plotted a graph of y against 1 over x squared, you would get a straight line, and that would confirm the relationship. You might try y is 1 over x, and then 1 over x squared, and then possibly 1 over x cubed, I don't know. But we're looking for a straight line, and the straight line would confirm the relationship. Nothing to do with graphs, but a very common exam question. There's another way of proving a relationship. If I'm suspecting that y equals k over x squared, then y times x squared should be a constant. So if I multiply y by x squared and look at the values I get, do I get the same value every time? Bear in mind kind of natural uncertainty and rounding errors and things like that. In this particular case, I would say yes, I do. All my answers are kind of hovering around 10. There's no overall trend of them getting bigger or smaller. They're all about the same. Okay, now pretty basic. When you do a graph, what needs to be there? You need to label your axes. You need to have units in brackets. You should have a sensible title. You should always plot your points accurately. They will be checked. If you're asked to plot a graph in an exam, they will check that you are plotting your points accurately. And then we do a line of best fit. The rule with the line of best fit is that you should be as close to as many points as possible. Notice that I'm ignoring an anomalous point. To me, that's obviously an anomalous point, and then my line of best fit is as close as possible to as many as possible. I try to have the same number of points above and below the line, and then with a ruler, a nice straight line of best fit. Very often we work out the gradient. I'm assuming this is kiddie stuff. The gradient is the change in y divided by the change in x. In this case, the gradient's going to be 0.88 meters per second. It's a distance time graph, so it's going to be velocity. Sometimes we have to get the gradient of a tangent at a point. That will tell us dy dx, the rate of change of y with x is the gradient of a tangent. One point I'd like to make here is be careful drawing your tangent, and when you do your triangle, do a big triangle. Don't do a pathetic little titchy triangle or you'll get a rubbish answer for your gradient. Draw a big tangent and do a big triangle, and that way you'll get something accurate. Uncertainty bars. I've always actually called them error bars, but I noticed the specification calls them uncertainty bars. If we know what the uncertainty is, then we can do these bars on our graph to express the uncertainty. And if we have estimated the uncertainty correctly, then our line of best fit should go through all of the bars, as it does in this case. You can have uncertainty bars on the x-axis or the y-axis or both, and you end up with this cross shape if you have them on both axes. We can actually use uncertainty bars if we are getting a quantity from the gradient of the graph. Then what we can do is a line of best fit and a line of worst fit. I've actually done 2 lines of worst fit, and if you get the gradient of the worst fit line, the line that just goes through the error bars, you can estimate the uncertainty in the quantity that you're getting from the gradient. This is very important. Y equals mx plus c. You did in GCSE maths. It's the equation for a straight line. And very, very often in physics, in experiments, we find quantities from the gradient of a graph. Y is what we put on the y-axis, what we plot on the y-axis. X is what we plot, Y is what we plot on the y-axis. X is what we plot on the x-axis. M is the gradient, and C is the intercept on the y-axis. And here are some examples that we will do in A-level physics to find the internal resistance and the EMF of a power supply. V equals minus IR plus E, and the gradient, if we plot V against I, the gradient will be minus R. The intercept will be the EMF E. We find the resistivity of a metal, we plot R against L, and then the gradient is rho over A. We get the gradient of the graph and multiply it by the cross-sectional area of the wire, and that gives us the resistivity. You will at some point get a value for little g doing an experiment with a pendulum. T squared equals 4 pi squared over g times L. If we plot t squared over L, then our gradient is 4 pi squared over g. And then we can also get a value for Planck's constant from a graph. Using LEDs, if we plot a graph of the voltage needed to get our LEDs to work, different colored LEDs, and do a graph of this voltage against frequency, then the gradient of the graph is h over E. We can get a value for Planck's constant.